webinar simplifying OBD use cases using one powerful diagnostic tester. It is not a hidden secret that onboard diagnostics is transforming. During the next 45 minutes, Softing Automotive will guide you through the most important details of SAEJ 1979-2 and -3. Furthermore, we will demonstrate OBD use cases using our development tester, Softing DTS.monaco. But first, let's introduce ourselves. 9 years ago, and typically I travel a lot to give on-site trainings about our diagnostic tools and the diagnostic standards. Mario, may I hand over to you?
Thank you, Bernhard. My name is Mario Bukowski. I'm working at Softing since more than 20 years now. I've started as application engineer, working on customer solutions and also giving trainings. Since 2008, I'm working in our sales team, and there my main goal is not to sell our products. What our customers need are solutions. And OBD is a very good example where our products can be used as a solution for a wide range of use cases. Here's the agenda for today. First, we will focus on the key changes to the OBD standard, which comes with SAEJ 1979-2 and -3. Next, we will go into a bit more detail and explain the basic concepts of OBD. Then we will start the demonstration of OBD use cases. And last but not least, we will have time for your questions. At the beginning of this decade, a significant change took place in the field of onboard diagnostics. The mandatory introduction of UDS services in OBD. For this reason, SAEJ 1979 has evolved into a multi-part series of documents. J 1979, which we all know as OBD in the past, has split into two different documents. It will be replaced by SAEJ 1979-2 for vehicles with combustion engines, and it will be replaced by SAEJ 1979-3 for zero-emission vehicle propulsion systems. Bernhard, there are different powertrain types. Can you give us an overview when 2 or -3 shall be used?
Yes, of course. On a higher level, both standards can be compared the following way. In SAEJ 1979-2, OBD on UDS, the focus is on emission-related components. In SAEJ 1979-3, CEV on UDS, the focus is on CEV propulsion-related components. On the right-hand side in this box, we see the powertrain types. And the following powertrain types must comply with OBD on UDS. The biggest group is internal combustion engines. Internal combustion engines followed by plug-in hybrid electric vehicles. They can be charged from the outside, but inside they also have a combustion engine, which must comply to OBD on UDS. And the same thing applies for hybrid electric vehicles. They cannot be charged from the outside. They have a smaller battery which can be charged by the combustion engine, but for homologation, the combustion engine part is important, so it must comply with J 1979-2. What about powertrain types that comply with J 1979-3 CEV on UDS? The biggest group includes battery electric vehicles. Battery electric vehicles followed by plug-in hybrid electric vehicles, so they appear also on both sides. As I told you, they can be charged from the outside, and they also have a bigger battery that must comply with CEV on UDS. And, not to forget, fuel cell electric vehicles.
Thank you very much. When will this be valid for the markets?
That's a good question. Well, for the United States, we have the following rollout plan. What we see is the US federal baseline path of J 1979-2 and -3. The blue curve describes internal combustion engines that comply with OBD on UDS. And we can see that in a single step, 100% fleet compliance is mandatory for model year 2027. The orange curve describes zero-emission vehicles and plug-in hybrid electric vehicles that comply with J1979-3. And a phase-in here includes 40% fleet compliance for the model year 2026 and 100% fleet compliance for the model year 2027. We already heard about the regulatory adoption of UDS services in OBD, but what is UDS? The ISO standard 14229-1 specifies 26 UDS diagnostic services and their semantics for communication between a diagnostic tester and an electronic control unit. UDS is widely used in manufacturer-specific diagnostics. It provides enough flexibility. We can execute an ECU reset. We can write data for variant coding. We can transfer data when it comes to flash programming, or we can control the actuators with routine control. But only the bold services are mapped to the new standards. So this is service ID 14, clear diagnostic information, service ID 19, read DTC information, service ID 22, read data by identifier, and 31, routine control. So these are the important UDS services for OBD on UDS and CEV on UDS. The benefit is convergence of legislated and manufacturer-specific diagnostics. We no longer have to distinguish between OBD modes and UDS services. Here we see the mapping of OBD classic modes to OBD on UDS. Mode number 1, for example, request current powertrain diagnostic data. This mode is mapped to read data by identifier with the UDS service ID 22. Or another example, mode 3, request emission-related DTCs. This mode is mapped to read DTC information with service ID 19. And another example, mode 8, request control of onboard system or test or component. This mode is mapped to routine control with service ID 31. What about CEV on UDS? On the next page, we see the mapping of OBD classic modes to CEV on UDS. It's almost the same, but the following modes are not mapped. That's mode 2, request powertrain freeze frame data. So there will be no freeze frame data. Mode 6 is not mapped, request onboard monitoring test results. And mode A, the last one, request emission-related DTCs with permanent status. They are not forbidden, they are just left out in the mandatory service list, which means OEMs can use freeze frame data or permanent DTCs, but the new standard CEV on UDS does not mention them. In direct comparison, J1979-2 and -3 show the following differences. As I told you, freeze frame data is supported in -2, but not supported in -3. Permanent DTCs are supported in -2, but not supported in -3. Routine control, the service ID 31, is supported in both standards. Well, in -3, it's available, but still without defined test routines. So there are no test routines at the moment for zero-emission vehicles. And what about the transport protocol? For OBD on UDS, so -2, we have diagnostics over CAN, so CAN communication. Regarding CEV on UDS -3, we can use both diagnostics over CAN or diagnostics over Internet protocol, which means we can benefit from higher data rates when it comes to Ethernet communication. So Mario, may I Heo, may I hand over to you?
Yes. In the next chapter, we will have a closer look what is OBD and give you a short introduction into this term. As far as I know, this photo shows an American metropolitan area in the early 80s. But one thing is very certain for me, I do not want to breathe there. The large number of not correct functioning exhaust emission control systems was identified as a major reason for air pollution. For example, catalysts were mandatory in the US since the year 1974. But what good is a catalyst for if it doesn't work proper? Respiratory diseases and acid rain had certainly reached levels that could no longer be tolerated. The basic idea behind OBD was that the vehicle automatically detects malfunctions before they lead to a significant increase in emission. For this, the vehicle continuously monitors its emission-related components. If any faults are detected, they are recorded in the fault memory, and this fault memory, along with other data, can be read by a regulatory authority via a defined interface. Here we see a small conclusion of different systems that are monitored by OBD, which are, for example, misfire, the fuel system, catalyst, oxygen sensor, and evaporative system. However, this raises a very interesting question. Why does OBD also exist for CEV, for zero emission vehicle? Why is a system like OBD now being extended to electric powertrains? No internal combustion engine, no exhaust gases. That doesn't make any sense, or does it? Well, if the battery's capacity declines or the charging system isn't working properly, then the efficiency goes down. More energy is pumped into the system than is needed for the drive. And even if this energy was generated from green sources, when it's wasted, it quickly loses its green status. Furthermore, electronic drive systems are high voltage systems. For this reason, it is important that these systems are also continuously monitored to protect life of driver, passenger, and of course all other people which come into contact with the vehicle. Bernhard, before we start with the demonstration, please provide us with the most important technical terms in OBD.
Yes, of course. What we see here is the header bar of our OBD user interface in DTS.monaco, and we have to talk about the following technical terms: diagnostic trouble code types, parameter identifiers, info type identifiers, and readiness groups. So first, let's dive into the diagnostic trouble code types. We can have the following DTC types in an OBD system. First one is a pending DTC. That's a fault detected only once. It's not yet confirmed. There is no activation of the malfunction indicator light, and it may disappear if it is not detected again. So it may disappear, but it can also turn into a confirmed DTC. That's a fault detected multiple times. It's stored in the ECU's memory. It can trigger the malfunction indicator light, and that's important, it can be cleared with a diagnostic tool. It can be cleared manually. What cannot be cleared manually is a permanent DTC. So a confirmed DTC can also turn into a permanent DTC. That's an emission-related confirmed fault. It is stored for regulatory purposes and cannot be cleared manually. It will be removed after a successful monitor verification. So let's assume the catalyst is damaged or needs to be exchanged. Then we have to repair it. And after this, we need additional drive cycles to have a successful monitor verification. Then the ECU software will remove the permanent DTC. And we're going to see pending DTCs, confirmed DTCs, and permanent DTCs in our application, in our demo. What about parameter identifiers? These are standardized identifiers used to request diagnostic data from a vehicle. They are also called PIDs, and the PIDs include live sensor data, status information, or monitoring data. They also exist in OBD Classic, and when we use OBD mode 1, then this is combined with a PID with a parameter ID. But in the new standards, we use the UDS service read data by identifier instead. It starts with the service ID 22 combined with a 2-byte data identifier, the DID. And the high byte of the DID is a prefix here. It can be F4, F5, or F7. And the low byte of the DID is the PID. So this is how we can see the old world in the new world. And let me give you an example for a PID in the case of zero-emission vehicles, CEV on UDS, the traction battery pack state of health. DID here is F4B2. And what is state of health? It's the ratio of the current capacity to the nominal capacity in the new condition, expressed as a percentage. And here we see an example, the diagnostic request, service ID 22, and then the data identifier F4B2. In the positive response, we have the service ID 62 because we add plus 40 according to UDS rules. Then we just mirror the DID F4B2 and FE, that's the actual value. And the interpretation of this value gives us 99.6% for the state of health. And such values are crucial for warranty decisions, residual value models, and the assessment of battery lifespan of zero-emission vehicles.
Bernhard, from my point of view, it seems that this state of health might be the new odometer value for used zero-emission vehicles in the future. Am I right?
Yes, exactly. In the future, when we buy a used electric vehicle, it will not be about the travel distance in kilometers. It will be about the state of health in percent. So this will define the price and the customer's satisfaction. That is correct. We also need more technical terms like infotype identifiers. These are standardized identifiers used to request vehicle information. For example, the vehicle identification number, the VIN, calibration IDs, ECU names, and so on. So it's more static or slowly changing data. And here we again use the read service, read data by identifier, which starts with service ID 22, followed by a 2-byte data identifier. And the high byte of the data identifier, the DID, is a prefix. Here it is F8 for infotype identifiers. And the low byte of the DID is the infotype identifier. And there is also an example for the request to read out the vehicle identification number, the VIN. It's service ID 22, followed by F802. What about freeze frame data? What about freeze frame data in SAEJ 1979-2? We already know that it is not supported in -3. And in UDS, we also call it snapshot data. Instead of freeze frame, we sometimes say snapshot data. And it is a stored set of parameter values like PIDs recorded when the DTC is set. So it's data from the past. It's data from the past. It's not live data. It refers to the time when the DTC was stored in the memory. And each snapshot is associated with a specified diagnostic trouble code, a DTC. And there are 2 DTC snapshot data records for the first occurrence and the last occurrence of the DTC. And here is an example. Let's assume the oxygen sensor fails. Then the ECU sets a DTC and additionally stores freeze frame data, which looks like that. Rotations per minute, 2,500. Vehicle speed, 80 kilometers per hour. Coolant temperature, 90 degrees. And later, much later, the tester reads the DTC and additionally gets the freeze frame data. And as I told you, freeze frame data is not supported in -3, but can still be used by the OEMs. And last but not least, readiness groups in the new standards. What is a readiness group? It is a collection of related monitors, so DTCs, and each monitor is connected to only one readiness group. The readiness group status can be completed, not completed, or not applicable. And the readiness group is only completed if all required monitors have run and finished successfully cycles since the last code clear. And that indicates whether the OBD system has completed its tests. And it is a DTC-based readiness. It's not just one bit. The DTC code and the DTC text gives us much more information where the problem can be found. And here is an example for readiness groups. One readiness group here is misfire. It includes 2 monitors or 2 DTCs. Both have the status completed. So misfire is completed as a whole group. It's different for the fuel system. There are 2 monitors or DTCs included, but at least one is not completed. So not completed is also the status of this readiness group fuel system. This is simple, it's more consistent, and globally applicable. So now it's time to demonstrate the OBD use cases with our development tester, Softing DTS.monaco. Let me show you some typical OBD use cases. ECU development. So let's assume we get the first ECU prototypes, and these prototypes, they need protocol validation, which means that we test these 4 services, service ID 22, 14, 19, 31. And the goal is to develop tester communication efficiently. Test automation is another use case, which includes automated diagnostic sequences of many ECUs. So we want to program scripts, and one example can be an intentional fault injection followed by validation of the DTC behavior. And the last use case is the compliance test, which is based on another standard, SAEJ 1699-3 and -5, which ensures compliance with regulations. And on this last slide, we see the setup for the demo. On the left-hand side, we see Softing DTS.monaco. On the right-hand side, we have Softing TCS device, which simulates the diagnostic communication of a vehicle. And our vehicle communication interface here is Winning 2000. So let me switch now to the demo. Let's see this setup in action. So now you should see the start page of DTS.monaco. I am connected here with Winning 2000. This is perfect. And now let's open this workspace here. Okay, we see the user interface for OBD here. This info bar on the left-hand side gives us the most important information, protocol identification, certificate requirements, the vehicle identification number, battery voltage, and so on. But the main diagnostic functions are located here. Here is the header bar that I showed you earlier, DTCs, PIDs, infotypes, readiness status. Let's start with DTCs. By just one click, we can read out the diagnostic trouble codes. This is how we simplify the OBD use case here. It doesn't matter if it is a single ECU or a car. By just one click, we get the following information from our simulation here. In a few seconds, we should be able to see the following result. This result is for all ECUs here. And what we get is a list of diagnostic trouble codes, trouble code texts, and for example, the status of each DTC. As you can see, we have pending DTCs, permanent DTCs, and confirmed DTCs. I can also change the view here. I want to see only the information for the engine control module, ECM. let's do this. There is one DTC involved here with the text turbocharger, supercharger, inlet pressure sensor A. That's the text here. And the status is pending. So we are looking at the pending DTC, which also has freeze frame data here. We have freeze frame data, for example, accelerator pedal position F, relative accelerator pedal position, or cylinder fuel rate. And as I told you, we have two snapshot records here for the latest and the first occurrence with slightly different values here. So that's what I wanted to show you about diagnostic trouble codes. Let's move on to see the parameter identifiers, the PIDs. It's also very simple, just one click, read all PIDs. And now we have to wait for this simulation result. So this is the full list. Here we see the PIDs or the data identifiers. And when I move to the engine control module, we see data like engine coolant temperature or engine RPM, vehicle speed sensor, and so on. In a similar way, we can read out info types. By just one click, we get the following list, which includes the vehicle identification number, the VIN, or calibration identification, calibration verification number, ECU text, and so on. Last but not least, we can have a look into the readiness groups, readiness status here. We click on the read button and get the following example. Engine control module, which gives us 5 readiness groups. I want to look into the evaporative system monitoring, which includes 3 monitors or 3 DTCs. One of them is completed, the other 2 are not completed, so the readiness group as a whole is not completed. And it's similar for misfire monitor. Here we have much more monitors, much more DTCs, but still one DTC is not completed. So this is also the status of the whole group. We can create a report regarding these diagnostic functions here. We can also read out everything by just one click, but we already have the results. So let's create the report. We save it and open it. Let me share now this document. Yeah, this is how it looks. This is how it looks. We have 4 entries here: DTC information, info type information, parameter IDs, and readiness group status. And when we check the details, we see, for example, the pending DTC about the turbocharger, supercharger. And in a similar way, we can check out parameter identifiers for the engine control module here, engine coolant temperature, and in a similar way, the readiness groups. Fire monitoring, that's what we looked at. Okay, great. Let me return to the DTS.monaco UI. In the next step, I want to change the simulation. So I will close this workspace for a few seconds. And now I have to work with the TCS device. I will remove a USB stick and use another one for CEV on UDS. So we just saw a simulation for a combustion engine, and the next simulation includes data of a real-life zero-emission vehicle. Takes a few more seconds to start the simulation, and I want to show you state of health, for example. This is a very important parameter. And then we will also have a look into test automation and the other OBD use cases. I'm still connected here. I'm still connected here to Winning 2000. That's important. This is our vehicle communication interface. And we will use the same project here, diagnostic test modes. Okay, now the simulation is ready, so let's click on it. And what you can see here is a first change, certificate requirements. Now we have light duty CEV. So this is a first proof that we have changed the simulation. And I can also show you new parameter IDs. So let's read all PIDs here. In a few seconds, we should get something like this. Yeah, I want to highlight battery management control here, which gives us the PID F4B2 traction battery pack state of health. Besides this OBD user interface, we can also switch to the expert mode. Here we have full access to the diagnostic database. We see all logical links, all ECUs, and all services. And for example, I want to navigate to the read data by identifier service read data stream. And I want to search for the state of health. So in a long list, I can navigate to traction battery pack state of health. Now we can see it here, traction battery pack state of health. And when I transmit this service, I get a result down here, 75% state of health. So here we have full access to the diagnostic database, but still we can simplify OBD use cases. Here I can configure a button that also reads out the state of health. So I don't need to navigate through any tree structure. I can just click on it and get the next value, 62.7%. And besides state of health, I can also execute more complex diagnostic tasks with a button readiness status here. So reading out the readiness groups, which gives us a long list of diagnostic trouble codes here. So this is the expert view besides the OBD user interface. And we already talked about another OBD use case, test automation. What we see here is a button in DTS.monaco and an output field. And behind this button, I can execute a so-called OTX script. OTX is the ISO standard 13209. So it's a programming language for diagnostic sequences. And with this OTX script, I can read out the state of health and I can interpret the value. Let me do this. When I click here, I get these values. Let's start with the highest value. So I will click again. State of health, 94% means optimal vehicle operation. So I don't have to think about the value. Is it okay or not? The OTX script helps me to interpret the result. And when I click again, I get a lower value, 75%, still drivable, but degradation. State of health, 63%, second life market. In this phase, the battery is not used anymore in a car. It can be used in a solar power plant or in a big charging unit. And when we reach even smaller values, below 50%, it's time to recycle the battery and to get back the raw materials. How is this programmed here? So how does this script look like? I can show this to you in our OTX Studio. OTX Studio is integrated in DTS.monaco and it follows the standard, the ISO standard. So let me click on it and let's wait a few seconds. And then I can share this new window. So now you should be able to see this development environment. In the upper left corner, we can manage OTX projects and scripts. Programming elements are taken from the lower left corner, OTX elements. And diagnostic data, so ODX data, diagnostic services. This information is shown here on the right-hand side. The programming happens here in the center part. I can open a communication channel to a certain ECU. Then we execute the diagnostic service. read data stream, and we configure the PID here, which is traction battery pack state of health. That's what we already know. And in the response, I'm interested in the state of health. It will be stored in a variable, in a float variable. And then I want to compare the content of this variable with limits. Is it bigger than 80%? Is it higher than 80%? Then we get this text optimal vehicle operation. Is it between 80 and 70? Then we get the text still drivable. Between 50% and 70%, we get second life market. And in all other cases, we go to recycling. And here I transfer the content to so-called screen variables, which are also visible in Monaco, and they can be used for the configuration of my output field. So this is what I did in the background. This is the script here. And now I want to return one more time to DTS.monaco. Let's talk about the compliance test. This is still under construction, but I can show you the look and feel of the UI, of the user interface. So it refers to J1699-3. And we are still busy with this use case. But when this is finished, we have an all-in-one tester for the OBD use cases. Yeah, and that's the last part of the demo. Now we can go back to the Q&A session. So we can now wait for your questions. Yes, here is the Q&A session. So now it's up to you. To raise any questions. What are you interested in?
Okay, yeah, we have the first question. Are OBD and SOVD compatible? Oh, this is a good question.
Yeah, that's a good question. Well, service-oriented vehicle diagnostics, the new SOVD standard, introduces seamless access through 3 powerful channels: in-vehicle, proximity, and remote. So we have a standardized remote access, and this opens the door to anytime or anywhere access to OBD data. So we don't need any physical connection here. And we can say OBD structures the data and SOVD delivers the access. So in the future, they can go hand in hand.
Okay, I hope this answers this question. Here we have the second question. What about Euro 7?
What about Euro 7? That's also a good question. Euro 7 specifies many things, but one of the core topics is onboard monitoring, OBM, onboard monitoring. So the vehicles are required to self-monitor and report whether they are staying within the legal emission limits. So it's not only about this is broken or this is damaged. We continuously monitor if the car stays within the legal emission limits. And it's also required to have a backend cloud, where this information is stored. And this data is collected, this OBM, so onboard monitoring data, is collected by an over-the-air connection, over the air. And it's good to have SOVD because it standardizes a remote access. So I would say OBD, SOVD, and Euro 7, they go hand in hand and will be very interesting topics in the future.
Great. Next question. What version is our DTS.monaco that we have used today?
That's easy. That's 9.4.26 here.
Okay. From what model year is the state of health for HV battery and OBD in the European Union? For what model year is the state of health for high voltage battery on OBD in the European Union?
Well, we we showed slides about the United States. They are the first ones. That's what we can say here. So it starts this year with CEVs. The other markets, they will follow soon. I think it's not totally defined. It's not 100% guaranteed, but within the next 2 or 3 years, they will also introduce OBD on UDS and CEV on UDS. So model years 2027, 2020, 2028, they will be very important for Europe, for China, Japan. So it's roughly in the range of 2 or 3 years. That's what I believe here.
Okay. And then we have a last question. Do you have any plans to support the MENA and North African region for the automotive dealers or third-party workshops?
That's a good question. Any information? Well, it is it is a standard. It's a worldwide standard. So standardized tools can be provided to markets that support the standard. So as long as the cars, fulfill the standard, the tools can be used to read out the data. So it depends more on the car than on the tester, because the tester is the first thing that is ready, and then the cars have to follow. Okay, do you have any information on wireless OBD and the impact deleting the OBD port in the future?
We'll have an authorities, for instance, in California, being able to read OBD data.
I think that refers to telematic control units. So maybe in the future there will not be a physical OBD port. That can be one scenario, and then everything is about safety. Euro 7 demands that the backend servers are located in the European Union. So it's not allowed to have the server in North America or somewhere else. So I think here the most important term is Euro 7. Euro 7 has to define that backend servers have to be located inside the European Union and can be accessed by the government, by the European Union.
Okay, I really like the next question for you as our trainer here. There will be more resources to learn DTS and OTX.
Yeah, that's great. On our webpage, we have a few dates, but I think we need more dates about DTS trainings and Monaco trainings. Well, you can always contact our sales colleagues, and I think I have a colleague right next to me who loves to send offers. Yeah, we offer web trainings, we offer on-site trainings, so feel free to contact Softing Automotive.
When you want on our webpage, you can also have a good overview about the different trainings that we provide for you.
Training formats and training dates can be discussed with sales and the training department.
Okay, then next question. Will the OBD and UDS function be part of a standard DTS installation?
Well, we are testing this database and project, and I think that's also a sales topic. Will it be included automatically, or will it be exposed to a certain price? I think that's a sales topic that needs to be discussed and defined. So I think for the time being, this is still open. I think, but that's an interesting sales question.
Yeah.
Will it be provided in every installation, or do we have to buy it? I think we have to discuss this internally.
and me from the sales team, I will ask our product management. I hope they have an answer, and of course we can give you this answer later.
Please contact us.
You can see here on the next slide our email addresses. Send us an email address, and then we can answer this question in detail. Recently, new regulations are coming defining OBFCM, OBMM with DID, PID are still not well defined. How does Monaco plan to handle such upcoming regulations?
Well, so far, I think we haven't implemented this. So this is still an open topic and important for us to know. But regarding OBFCM and OBMM, we cannot give an answer at this moment, but hopefully in the future.
Mm-hmm. And the last question that we think can answer today, what is the tester address of the Softing DTS tester? Does it follow the SAE standards for Diagnostics on CAN? 11-bit or 29-bit CAN identifier and Diagnostics over IP. So it can be classified as a generic scan tool when connected to the OBD port in a real vehicle. Or is a Softing DTS tool used only for simulation and bench testing?
It can be seen as a generic scan tool.
Yeah.
It can. So we use the simulation here for the webinar, because we don't have space for car, but we are testing this UI with real cars. That's where we got the simulation from. It was generated by or from a trace, and you are right, it's a generic scan tool for OBD use cases.
And I think the tester address can be defined via the communication parameter set, yes?
Well, actually, here it is according to the standard. Okay. Here it is according to the standard. Otherwise, it would be a manufacturer-specific tool. That's not what we want here in case of OBD. So this goes hand in hand with the expression generic scan tool, generic OBD scan tool.
Great. Yeah, I hope there was something for everybody here now today in this short webinar regarding the topic OBD. Thank you very much for your time. You can see here again our email addresses from Bernhard and me. Please write us your questions and contact us if you have any question. Do not hesitate to contact us, and thank you very much for your time.
It was a pleasure. Maybe we'll meet again in the training. Bye-bye. Bye-bye, everybody.